Hi, everyone. Welcome to class. The topic today will be section 1.1, matrices and vectors. It's also the first video of the class, so we'll take it a little bit slowlier. I just want to make some general comments at the beginning of what we're going to be doing in this class, essentially what the goal will be at the end. And the real goal of linear algebra, per se, is to develop a new way to tackle algebraic linear systems. We've been working with linear systems for a while. Here's a little example of one. A linear system is just a set of equations where the variables appear in linear terms, meaning no exponents and meaning there's no exponents in them. I can give you another example of a linear system. We'll be dealing with something maybe slightly more elaborate. We could have more variables and more equations. 7, that's a perfectly fine linear equation. 2x1 plus 3x6, why not, is equal to 5. And then x1 plus x2 plus x3 minus x4 plus 2x5 equals 0. So you can see that the sizes may change a lot. This linear system here has 2 equations and 2 variables. And the one that I just made up here happens to have 6 variables and 3 equations. It is to work with stuff like this that will develop all of a whole new language and a whole new theory. And the main characters of that language and theory are going to be matrices and vectors. So that's going to be the starting point of our journey. For us, a matrix will just be essentially a rectangular array containing numbers. So whenever I'll say a matrix, I'll just mean a rectangle, a little table. And in each entry of the table, there will be one numerical value. Rectangles have sizes, height and length. Similarly, matrices have sizes, which are the number of the entries they have. We'll draw an example in a second, but one thing that you want to keep in mind throughout this class and for all the future mathematics you'll encounter is that the size of a matrix is written like this, m by n, where the first term is the number of rows of A, and the second term is the number of columns of A. Let's just jump into an example. How will, for example, a 3x2 matrix look like? I'll give them name. I'll call this one A. 3x2 means that it has to have 3 rows and 2 columns. So something like this is a rectangular array of numbers with 3 rows and 2 columns. That's a perfectly fine 3x2 matrix. Sometimes when I want to emphasize the size of the matrix, maybe I'll write it down here. How does a 2x2 matrix look like? Something like this. It's a square. A general 2x2 matrix, if I don't want to leave terms specified and I want to keep things as general as possible, will look like this. It will have 4 entries, and I'll use letters for them. Why not? Just one last example. I'll write down one more. Our matrix D. This time it has 2 rows and 3 columns. So it will look something like this. Okay. Another piece of terminology that we will use and you need to be familiar with is the entry of a matrix. So you see that a matrix is an array of numbers. Each one of those numbers is called an entry. what we want to do is to be able to identify an entry precisely and univocally. So whenever I'll write something like this, a double index here, this will mean that I'm looking at the entry that is in position 2 and 2, 3. That means 2 is the number of row, and 3 is the number of columns. Let's just do an example from above. If I look at my matrix D, and I want to look at the entry, for example, this entry here, that's going to be the entry 2, 2, because it's in the second row in the second column, and that's 4. Why shouldn't we write this in green? I'll pick another entry. Maybe I'll look at this 6 here. To identify 6, I need to be first row, third column. So 6 would be D13. And so on and so forth. Let's do an example with our matrix A. The 0 here is in the first column. It's in the second row and the first column. So I'll write that A, second row, first column is equal to 0. Okay, that's how the notation will work. What can we do with matrices? Essentially, you should think of a matrix as a very more generalized way to handle numbers. So we can do some of the operations that we can do to numbers. For example, it's very possible that we can multiply a matrix by a scalar. And allow me to just keep using this matrix here for sake of our example. I'll put it here. Maybe I'll erase that. I can multiply it by a number. Whenever I say scalar here, I mean a real number. So for example, I can write down 2a, and that's what I get by taking all the entries in A and multiplying them by 2. So when I write this, what I really mean is 2, 0, 4, 8, 10, 12. You can do that for any number. For example, I can write minus a, and that's going to be whatever I get by taking a and multiply every entry by -1. -5 and -6. Just like with numbers, we can multiply matrices by a scalar number. Another thing that we can do with them is to add them together. However, there's a warning here. We can only do this if the matrix is of the same size. We cannot add together matrices with different sizes. And you'll see in a second why that only makes sense. Let me take our matrix as above. 0, 2, 4, 5, 6. And then I'll take another matrix. I'll make it up. 7, 2, -1, 0, 2, 4. When I add these two matrices, notice that I picked the same sizes. Then their combination will be, their sum will be the matrix whose entries are the sums of the entries of these matrices in corresponding position. What do I mean by that? A plus B will be, again, a 3×2 matrix whose entries will be 1 plus 7 up here. Then I'll have 0 plus 2, 2 plus 6, and then 4 plus 0, 5 plus 2, 6 plus 4. I'm taking every one of these entries here and I'm adding it to the corresponding one in B. I wrote it out loud, but we will get fast at computing this sort of things. Just for this time, I write out every step. But that's what A plus B is by definition. Now that we have these two operations that we can do with matrices, let's just pause for a second and think about all of the properties of sum and multiplication by scalar that we really like when we work and we use them with real numbers. A lot of those properties will generalize and carry over to the setting of matrices. Here's a table. It's taken from your textbook. We can just quickly go through them and nothing should be surprising. For example, matrix addition is commutative, meaning that the order in which I add two matrices does not matter. A plus B is equal to B plus A. It's associative, meaning that if I'm adding more than two matrices, I can add them in the order I want. I can either add A plus B first and then C, or I can add B plus C first and then A. This matrix O here denotes the matrix whose entries are just all zeros. And these properties C's and D reflect what you would expect to get when you're working with a zero with respect to the sum. If you add the zero matrix to a matrix, you get back itself. If you add the opposite of a matrix to itself, you'll get a matrix whose entries are all zeros. The last three properties involve scalar multiplication. E just says that if I'm multiplying by a product, I can multiply by one scalar and then the other. F and G are distributive properties for multiplication by scalars. The scalar multiple of a sum is the sum of the scalar multiples, and scaling by a sum is the same as adding the two rescaled matrices. Here's a new operation that we can do with matrices, which we could not do with numbers. This is a new operation. It's called transposition, or alternatively, taking the transpose of the matrix. If I give you a matrix A, then you can take its transpose. It's denoted A with a little t, where we usually put exponents, constructed as follows. The columns of A transpose are the rows of A. Or, like it's written here, the rows of A transpose are the columns of A. So if I were to compute A transpose in this example, I need to take, well, we said the rows of A transpose are the columns of A. So the first column of A is 10, 7. Maybe let me highlight it a little bit. Then the first row will have to become 10, 7. The second column of A is 11, 0, which means that the second row of A transpose will be 11, 0, and the third column of A is 3, 9. A transpose will have 3, 9 as its third row. You can think of it like this, or alternatively, you can think of turning rows of A into columns of A transpose. You can see that the first row, 10, 11, 3, has become the first column, 10, 11, 3. It's equivalent. Let's play with it a little bit more. So in these examples here, if I want to take the transpose of this matrix, well, let's see. The first row, the first column of B will become the first row of its transpose. The second column of B will become the second column, the second row of its transpose. Sorry about that. If I want to take the transpose of a general 2x2 matrix whose coefficients are unspecified, A, B, C, D, what I get is as follows. AB is a row, it now becomes a column. CD is a row, it now becomes a column. So what I effectively did was to switch out these two. That's what the effect of a transposition does on a 2x2 matrix. It leaves elements on the main diagonal fixed and it swaps the other two. We'll say more about that in a second. I want to bring your attention to the fact that by how transposition works, the role of columns and rows gets switched, and therefore the sizes of the matrix get switched. If a matrix has m rows and n columns, its transpose will have n rows and m columns. Let's write it down in this example here. Matrix B has 3 rows and 2 columns. B transpose has 2 rows and 3 columns. Well, C is a little less interesting in that respect because it's a 2x2. When I transpose a square matrix, I get a square of the same size. Okay, let me just comment briefly on properties of a transpose. Transposition works well with the operations that we've already seen, addition and scalar multiplication. In fact, the transpose of the sum is the sum of the transpose. That's what property A reads. If I multiply a matrix by a scalar and then I transpose it, that's the same as transposes and then multiplying it by a scalar. And taking the transpose twice gives me back the original matrix. That's not surprising. If you think of a matrix and then you transpose it, so you symmetrize it like this, and then you do it again, you end up with the matrix that you started with. Okay. Transposition allows us to define a very special class of matrix, which is that of symmetric matrices. We say that a matrix is symmetric if it's equal to its own transpose. Here's a few examples of symmetric matrices. I welcome you to try and compute the transpose of these 3 matrices, but you'll see that essentially what the transpose does is to switch these 2 entries in this case. It will switch these 2 entries in this case here, and here it will just send the first row, second column to the second row, first column entry. So it will match up the 2 with the 2, the 3 with the 3 over here, and 4 with a 4. So although symmetry has this slightly complicated or slightly abstract definition, in practice, it's really simple to recognize a symmetric matrix. You see that in all of these cases, there's a symmetry along this diagonal. And it doesn't matter what the entries are on the diagonal, because they only need to be equal to themselves according to this A equals A transpose condition. But everything that is not on the diagonal needs to be symmetric and reflected across. So if you look at the examples of symmetric matrices that we've just seen, you probably notice that they are all square. And in fact, it must be that a symmetric matrix is square. Remember that the size of these matrices in general gets switched out. So the only way that an M by N matrix is the same as an N by M matrix is that M is equal to N. In other words, A and A transpose must be square. That's the content of this note up here, but I want to bring your attention to the fact that the converse is not true. it's not true that every square matrix is symmetric. Examples are easy to find. If I take this matrix here and I transpose it, I get a matrix that is not the same as the one that I started from. Okay. Let's try to use some slightly more general language. This is something that will appear in the future when I will want to write a matrix without specifying its coefficients. I will write it just like this. I will just leave every entry as indicated by its position, but I'll use a letter to denote it. So how does a general symmetric matrix look like? If I take any random matrix denoted like this with this abstract notation, then symmetry just means that whatever entry I have in the ith row and jth column must match whatever entry I have in the jth row and in the ith column. Written shortly is just this condition down here. Aij must be equal to Abi for all of indices I and j that range between 1 and n in both ways. And here's a little fact, and we'll use it to play around with a few general matrices. If I give you any square matrix, there's a way to cook up a symmetric matrix from it. And that way is to just add its transpose to it. So for every square matrix, A plus A transpose is symmetric. Let's just check it for a few cases. We can do the 2 by 2. I'll take a general 2 by 2 matrix like this. I'll call this A. And then I can look at A transpose. Oops, this is a B. And then I can look at A plus A transpose. If I add these two together, I get 2A, B plus C, C plus B, 2D. But now, well, B plus C and C plus B are the same. So this is symmetric. Okay, now we're ready for the general case. If I give you a general matrix like this, then how will its transpose look like? Well, its transpose will have entries with the roles swapped. So the first row of A will become the first column of its transpose. So the entry in the transpose will be the following. The entry that was in the first row of a second column, and that's what this 1 and 2 signify, will now be in the other place. Oops. The entry that in the general matrices sits in the first row and third column, in its transpose will sit in the third row and first column. And then we can go all the way down to A1n. We can play the same game for the second row. The second row of the matrix, maybe we can quickly scroll back to the general form of the matrix. You see the second row will have all entries whose first index is a 2. Because the first index denotes the row. So the second row of our matrix, I wrote a couple more entries here, will become the second column of the transposed matrix. And you start to see how this goes. In the matrix A, every column has constant second index. When I transpose that column, it becomes a row. So my first row will end with the entry AN1 from matrix A. So all of the entries get swapped in places, which means that now when I take, we can finally look at A plus A transpose. Well, let's look at the two matrices that we have above. The first entry, first row and first column, will gain A11 from both matrices. Then when we sum entries in the second row and first row and second column, we will get A12 from A plus A21 from A transpose. Let's have a look at the second row and first column as well. There too, I have A21 and A12. So writing them in a slightly different order, well, we get the same, A21. On the main diagonal, I get A22 on both sides. When I continue on this row, I will have A1n plus AN1. Down this first column, the last term will be, again, A1n plus AN1. So on and so forth. This last here will be 2ANN. So the entry, I'll write it like this, and let's see if you like this notation. If I look at the matrix A plus A transpose in position ij, so the entry in the ith row, jth column of that matrix will be Aij plus Abi. But that means that it is the same as the entry that we are bound to find in position ji. If you think about it, ith row, jth column will have this entry here, but also jth row, ith column will have the same entry. We did one little example up here with I and j equals respectively to 1 and 2. I equals 1, j equals 2 up here. In other words, A plus A transpose is symmetric. Okay. The next thing that we're going to talk about today, and this is going to be the last topic for this video, is vectors. I've been telling you what matrices are. Vectors are nothing but special matrices. In particular, vectors are matrices with exactly one row or exactly one column. We'll denote them something like this. I'll just use a little example. This vector V is just a matrix with 3 rows and 1 column. That's what makes it a vector, because it only has 1 column. We can also have row vectors, and I'll write those in the following way. This is a row vector with just 1 row and 4 entries. Sometimes we'll write row vectors in the following way. The same vector u, depending on the context, may be written like this. There's going to be a slight distinction, but I want you guys to know that in the literature, both writings are acceptable, and they're usually interchangeable. Okay. Why is it important that I point out this other way of writing it? Is that you probably have seen something of this writing before, something like this vector u here. In fact, we can think of vectors as geometric objects through thinking that every one of their entries is a coordinate in a certain space. When we have a vector, for example, this v over here, whose entries are 1 and 3, first of all, there's some terminology involved. We say that that vector is two-dimensional, or that the dimension of v is 2, because that's the number of entries it has. Whenever we have an n-dimensional vector, we can draw it in n-dimensional space. Now, this is a two-dimensional vector, so we can definitely draw it in a two-dimensional plane, which is R2. And sometimes, well, you may have seen vectors drawn there, but written in the notation of the parentheses. So if I were to draw that v, it will have a 1 in the x coordinate, and then a 3 in the y coordinate. So v could be drawn in a few different ways, but we'll usually use arrows to denote them. So that's my vector v, plotted in the plane. Let's do the same thing with this other vector u. This has x coordinate 3 and y coordinate 2. So u lives in the plane and it sits somewhere around here. Oops. Not only can we plot vectors in the plane and understand them as geometric objects, but we can understand operations between them as geometric operations. Let's have a look at an example here. I have this vector v. I'll plot it again. It's 3, 1. It's not the same as before. So v lies somewhere around there. And here it goes. I can make sense of vectors 2v and minus v. How? Well, let's maybe write them down to just try to understand what they should look like. The vector 2v is a vector 6, 2. When I try to plot that here, I get 6, and then I get 2. 2v lies there, which is exactly on this line that contains my vector v. It's on that line, and it's a stretching of v by twice its length. So the length of the vector 2v is twice the length of v. Multiplying by 2 is the same as stretching by the similar factor. When I look at minus v is the vector minus 3, minus 1. It will still be on the same line, but this time it will be pointing the other way. So minus v is a vector that points down like this. Okay, last but not least, it's how can we understand addition of vectors? Let me just remind you that these vectors here are 3, 2 and 3, 1. I'll draw this a little bit out of scale just to make the picture a little easier. These two vectors here, I'll plot them. We said v is here and u maps up here. Let me give them names. This is you. So we can definitely compute their sum algebraically. That's going to be 6,3. But we can also use our picture to get an idea of what that sum will become. The way we do that is by using what's called the parallelogram law. So what I've done here is to take a copy of V, oops. So take a copy of V, no. That was a boo-boo. Okay, my application here just crashed, but let's pick it up from where we were. We had the vectors V and U. When I sum them together, the way I can graphically understand that is that I get a copy of V and I attach it to the endpoint of U, and I complete that parallelogram with a copy of U attached to the endpoint of V. This is also called the parallelogram law. Exactly, because addition of vectors corresponds to building a parallelogram, two of whose edges are the vectors that you're trying to sum. This is the end of section 1.1, and I'll see you at the next video.